Pranams to all the elders here and greetings to the students. It's rare to see so many students in a talk on Indian knowledge system. So Professor Deshmukh and the organizers have to be really felicitated and congratulated for this. ठीक है तो इसको निकाल दें नहीं आप दोनों लगा सकते ठीक है तो I will try to mostly address the students except for few occasional points. So first is why do we need Indian knowledge systems? Why are we talking about it today? So that is something that our students should know. Then I will say something about how in the higher education scheme, like in the courses that you are studying, we incorporate Indian knowledge. That's for the organizers here to implement. Then in a brief time, because merely talking about Indian knowledge system is not going to be very useful to you, I will give you some overview of what Indians did in astronomy and mathematics, so that at least you will know the names of 20-30 persons. Perhaps you may know the names of 5-6 of them. But you will also know, you will be able to say at least one sentence about what they did. So that's very important. And lastly, I will say something about what we can do in school education, if I have time. So what is Indian knowledge? So Indian knowledge is all the systematized disciplines of knowledge which were developed to a very high degree of sophistication in this country from very ancient times. And all the traditions and practices which the various communities in India, including the tribal communities, have evolved, refined and preserved. So to know Indian knowledge, you not only have the ancient books, but you also have remnants of ancient artifacts. You also have the people who have inherited that tradition and practicing it. So all these are sources of Indian knowledge. Now, till the early part of 19th century, this was the only knowledge that was prevalent in India. Until then, they were actively practiced and innovated upon. There was no period of total stagnation. There were some periods of up and down. They contributed immensely to the prestige of India and immensely to the well-being of our society. And it ensured that India was a very major economic power till early 19th century. So during its long civilizational history, India must have undoubtedly borrowed lots of things from other civilizations. But that doesn't make Indian knowledge a khichdi. It is not a mixture of India, Islam, Christianity, East, West. At the core, it was Indian knowledge all through. It was only in early 19th century that there was a total disruption of Indian knowledge system. And so we are in a situation called, in our own terminology, it's called Sampradaya Vichitra, a discontinuity of our continuous evolution in a certain knowledge stream. But today, we are 200 years away from early 19th century. So during at least the last 150 years, a lot of work has been done by many great Indian scholars and even some foreign scholars also. You heard two names, Henrik Kern and Pandit Sudhakar Dwivedi. Sudhakar Dwivedi edited about 30 to 40 texts of Indian astronomy and mathematics towards the end of 19th century. So it is true that a lot of work has gone on, but what's very important to realize, this not only for the students, but all the scholars here, that what we have today cannot be said to be a comprehensive understanding of the history, of the methodology, of all the concepts of Indian knowledge. Because if you just take the history of last 60, 70 years, What we did not know about many disciplines of Indian knowledge, even in mathematics or astronomy, etc., and what we know today, there is a great jump, great advancement. So in that sense, we seem to have missed a lot of what we knew 200 years ago in the course of having discontinued studying it. So why is it so? It's mainly because all our knowledge, what is called our traditional knowledge, or civilizational knowledge, went out of the regular institutions of learning. And even those people who had to do all this work, they had to do it on their own, either individual initiative or at the margins of these institutions. So because most of our knowledge went out of not only institutions of higher learning, it went out of all our schools. A simple example is 90% of the mathematics that we study in our school, arithmetic, algebra, geometry, trigonometry, most of it either originated in India or was developed very systematically here. And the rest of the world had to learn it from India, either in 8th century or 10th century or in 15th century. But when we study mathematics, we study it as a totally alien subject. We don't even know who did what, where did it all come from. Whereas when we study this discipline in later times, we will hear so many names. We will hear the name of Euclid, we will hear the name of Pythagoras, we will hear the name of Newton. So this is the kind of situation. Now, therefore, if we want to say we are wanting to see a resurgence of Indian civilization, it's very essential that we should be very thoroughly grounded in Indian knowledge. And just as we did in all the earlier centuries, we can borrow anything from any other source of knowledge. But our grounding should be in Indian civilizational knowledge, values. Based on that, we are able to adopt, take for ourselves, and even innovate upon. The main reason we are not able to innovate upon modern scientific knowledge is we are not only borrowing that knowledge, we are even borrowing the institutions which are used to organize that knowledge in the way they have done. And most of it will not work for us. And therefore, and we don't know the background of those developments that have gone on there, the motivation by which much of this knowledge is generated. So, for us to be a creative civilization, for us to be called as representatives of Indian civilization, most of our activities will have to be informed by and grounded in. Since we don't teach Indian knowledge as a regular part of our curricula, most of us are not exposed to it, and therefore we are not in a position to creatively bring it into the fore in making any innovations and even update our older knowledge for contemporary needs and purposes. So all this is sort of well known, but we have not acted upon it. The new educational policy was one document which tried to sort of tell us we should move fast in this direction. Two most important things in new education policy, which we are yet to follow systematically, are the two. One is research on Indian knowledge should be among the mandated tasks of all our institutions of higher learning. So still that's not the case. There are 10 institutions here which have a small cell in Indian knowledge system, or there are some departments where some work is going on. But this sort of a position that we need to go to, at least in 5 to 10 years. Second, Indian knowledge should form an essential part, not the whole of, but an essential part of the curricula taught in our schools, colleges, and all institutions. That's also not yet happening. Why am I saying this? Because the purpose of higher education really should be to imbue the youth with values, knowledge, and skills that will help them to proudly and knowledgeably manifest Indian civilization in the modern world. That is, It's not merely to say I'm proud of being an Indian. It's not merely to say our ancestors did all great things. You have to know how they did it, what they did. Then only you can claim to be an inheritor of that civilization. And it's that kind of an education and even fundamental values like the Indian understanding of the oneness of all creation. So this is not something that every civilization in the world can manifest that idea. And therefore, that will not be at the core of the knowledge of all civilizations. So while there are civilizations and civilizations, the knowledge generated by them may be universal in terms of application, but it will not be universal in terms of its acceptability, its values, its purposes. So it's all these factors that make it very, very important for us to realize that we need to make Indian knowledge really re-pervade our society as it was 200 years ago. It's not only about India. Say somebody talked about the dark ages of Europe. So how did Europe come out of the dark ages? We all know Europe borrowed extraordinary amount of knowledge and technology from China, from the West Asia, and perhaps even indirectly from India. But they sort of assimilated it into their core civilizational framework, which was essentially based upon the Greek-Roman civilization and the Christian religious worldview. It was the assimilation which brought into fore what we today call as the modern science, modern social science, modern world order, modern West. And so at the core, modern science and technology is a continuation of the older Greco-Roman and Christian civilizational science and technology in a modern form. Many, many countries in the world in the last 30, 40 years, they have of course adopted, like us Indians, the sciences, even the methods of organizing politics, society, all technologies. But many of them are trying to refashion them such that they are assimilable with the core values of their civilization. They are in continuity with their core ideas and knowledge, especially in social sciences, but more and so in all disciplines. For instance, in the last 30, 40 years, the Chinese have come up with a 15-volume sort of understanding of their own contributions in astronomy. Like that, in every manifestation of their public activity, they would like to link what they're doing today with the way China had developed. There's a very famous Japanese mathematician who has worked on Indian mathematics. So at the preamble of all his work, he puts in his own website something very clear, a very simple understanding, which is perhaps missing in Indian discourse. What is this simple understanding? He says that from the Edo period, which is about 17th century, Japan has been following the Western societies for all knowledge, including science, technology, and social thought. Now, the modern Western development in sciences are based upon the understanding of nature and the approach to nature that modern Western society developed. And in that sense, they can neither be thought of to be absolutely true, nor universal, nor should be the essential component of a future science, like today people were talking of a new meta-science or whatever. And it's therefore very essential that we should, Japan had been traditionally following the sciences and social sciences of China and India, so we need to really know all this. So this is the general kind of philosophy. Okay, now we come to specifics. So the new education policy really mandated that we should know all this. So what did Aryabhata, Varahmida, Sushruta, Charaka, Bhaskaracharya, Brahmagupta, Chanakya, Chakrapani Datta, Madhava, Panini, Patanjali, Nagarjuna. So we should learn all that these people did in all those disciplines. These should not only be nurtured and preserved for posterity, but also researched, enhanced, and put to new uses through our new education system. So I wish this happens during our generation. So in following this, UGC tried to organize a scheme for introducing Indian knowledge in higher education institutions. And this, sometime around March, they brought out the guidelines. And what is UGC sort of mandating? That every undergraduate student should at least take 5% of the total mandated credits in, they are using the word Indian knowledge system, Bharatiya Jnana Parampara, whatever you may call it. And at least half of this should be in the part of Indian knowledge which is related to the major field of specialization. So if you are studying commerce, you should know about how India performed commerce, what was the economic thought of India. If you are doing mathematics as your major, you should know how mathematics developed in India, to the tune of at least 2 to 3 credits of your major course. And everybody should take a foundational course on Indian knowledge system so that they know something about what India achieved in every aspect of human thought, human endeavor. So this was mandated and put on the UGC website in March 2023, but has not been yet put into action. For PG programs also, the same thing was mandated by UGC, that 5% of the credits should go in the IKS disciplines which are related to. If you are doing biology, you should study what did India doing. If you are doing engineering, same way. And even about courses which are related to Indian knowledge systems, like we have courses in philosophy, where most students may be studying Indian philosophy. We have courses in music, where most students may be studying Indian music. We have courses in Ayurveda. But even here, and many of the Sanskrit, I think there are about 15 to 20 Sanskrit universities, where most of the disciplines are traditional Indian disciplines. But even here, what has been happening is that most of these subjects have been, there is an attempt to relate most of these subjects and teach them in Western epistemologies and methodologies. It's not that we need not use Western epistemology or methodology, but we have been entirely basing all our studies on them. So even our historical methodology, our looking at this, so many times we say evidence-based. So what is evidence-based? This is an issue which has been very widely discussed in Indian books. The entire subject of epistemology in India, Nyaya Shastra, deals with what is evidence, what are the possible evidences, what will make a statement acceptable, what will make a claim acceptable. So while many of these Western epistemologies may be required, the perspective and the main emphasis of all the courses will have to be related to the basic perspectives of Indian knowledge. So with this I have stopped the broad outline. Now I will give you a brief summary, about 5-10 minutes, of how astronomy and mathematics developed in India. So it all goes back to the Vedas. Vedas are not texts about mathematics. They are not texts about modern cosmology. They are not texts about cognitive science. They are texts about how Indians conceived creation and how humans have to live in this creation to be able to realize their essential unity with all creation. But they have a lot of information from which we can understand how various disciplines developed under this larger philosophical perspective of India. So they have a lot of things about large numbers, factors, fractions, sequences, the decimal place value naming of numbers, which is very unique to India, and the idea of Shunya, which is zero, idea of Purna, which could be related to infinity, and perhaps to many other things also. There is a lot of observational astronomy in the Vedas. The 27 Nakshatra system comes from that. The Vedas have a record of Indians of having observed a star at the point of North Celestial Pole. North Celestial Pole is the point in the sky to which the Earth's axis points. Many times there may be no star there. But in 3000 BC, there was a star which was located there, and the text Taittiriya Aranyaka talks about that star. And it's also mentioned in some Puranas and all that. So that was the original Dhruva that Indians observed. But after about 2000 BC, there was really no star near the point where the north direction, the Earth's axis points in the north direction. There is no star there. This is because of a phenomenon called precession of equinoxes. Anyway, so we now have a star, and that is called Polaris or Alpha Ursa Minoris. And this has been at the north celestial pole only in the last 200-300 years. Similarly, there are instances of texts which talk about 1800 BCE. Then there are many, many ancient archaeological sites which will reveal in their construction, in their orientation, lots of astronomical information that we knew at that time. Now we are beginning to start having texts post-Vedas. This Parashara Tantra has been actually not, the original text is not available, and it has been reconstructed from various commentaries. And the main commentary was what Professor Ram Subramanian was mentioning, what is called Bhattotpala's commentary on Brihat Samhita, which was written in 6th century. But that text is quoting extensively from Parashara Tantra. And so you know, around 1350, we had a system of measuring the motion of celestial bodies, not by Rashis as we know today, but by nakshatras. The 27 nakshatras provided the scale to understand where the sun was, and the 6 seasons, planetary periods, eclipses, all that were discussed in that framework, and many comets were discussed and called, and they are also there in the Vedas. Now we come to the first oldest text of mathematical astronomy, not only in India but in the entire world. That's called Vedanga Jyotisha or Arka Jyotisha. It gives a set of algorithms for computing what is called the Tithi and Nakshatra. I will not explain what it is. Professor Shriram may tell you. By using the method of rule of 3. So using the method of rule of 3, assuming the mean motion, you calculate over a period of 5 years. So this is the first text giving algorithms for calculating the positions of celestial objects. It's dated to 1200 BCE. I'm sorry about that CE. This should be before the Common Era. And this is indeed the oldest text of astronomy. Now we can go faster. Then we have the oldest text of geometry. These are called Shulva Sutras. They contain the first statement in anywhere of a theorem of mathematics. And today that theorem goes by Pythagoras' name. But that is stated in Shulva Sutra. It is stated in the following form. The square of the diagonal of a rectangle is the same of the sum of the squares of two sides of a rectangle, which is what you recognize as Pythagoras' theorem. Its first statement occurs about 500 years before or 300 years before Pythagoras in Sanskrit. And that's one of the earliest statements of a general mathematical theorem in the world mathematical literature, though we don't recognize it as such. Just as Vedanga Jyotisha was the first text of mathematical astronomy, this is the first textbook of geometry. Then we have other texts, and then we come to one of the most important texts of India called Panini's Ashtadhyayi. This is at the fountainhead of whatever we do in computer science today. It's a text full of algorithms, and it tells you various rules and whatever you do in a computer program as to how various instructions have to follow one after the other, and how a loop will come, how you have to go out of the loop. All those kinds of techniques are there in Ashtadhyayi. And the purpose of Ashtadhyayi is, of course, linguistic, to derive all words of Sanskrit from what is called the base form and adding pratyayas. Then there is another very great text of ancient period called Pingala's Chandas Sutra. In Chandas, we have only two kinds of syllables, what is called the Laghu and the Guru, the short and the long. And every meter is a sequence of Laghu and Guru. And therefore, you have binary sequences. And so the entire mathematics of binary sequences and converting decimal numbers to binaries and binaries to decimals, and even computing powers and binomial coefficients, there are very, very beautiful algorithms in this book called Chandas Sutra, written in 300 BC. Now still we have finished the ancient period. I will now come to the classical period. The Bauddha Jaina texts have a lot of mathematics. The crucial development of arithmetic was by the adoption of 0 into the decimal place value system And this happened sometime between 300 BCE to beginning of Common Era. So once we had the decimal place value system, we could deal with numbers as we wanted. But now most of our texts were in the poetic form or in the sutra form. So writing number 3560 in a verse or in a sutra or 15,473 will be very cumbersome. So we discovered two methods to represent numbers in terms of linguistic phrases. One was called Bhuta Sankhya, where you use something like Netra or I to denote 2 or Veda to denote 4. Another was something called Katapayadi, where the various consonants stood for various numbers. And in fact, this made it very easy to write down entire mathematics or even any other subject in terms of wherever numbers came. In fact, in India, numbers came almost in all disciplines. So these were at the basis of that. Then there are various astronomical siddhantas. And there's something called the Bakshali manuscript, which was discovered in Rawalpindi, near Rawalpindi. This is also a very ancient text. And it's one of the most ancient manuscripts of India. Currently, it's in Oxford Bodleian Library. Its dating has been somewhere between the 1st century to the 4th century. Some of the leaves of this manuscripts are in the 1st century. Some of the leaves of this manuscripts are in the 4th century. But this contains all mathematical symbols, and it's a text of mathematics, and you can see how mathematics in India was being performed in 4th century. Now we come to the actual classical period. The earliest sort of text in classical period is Aryabhatiya. In 120 verses, he has given almost all of the basic elementary arithmetic, algebra, geometry, trigonometry. He was the founder of trigonometry in 30 verses. And in 90 verses, he has covered the whole of astronomy. Of course, the text is very difficult to understand merely by itself, so there are lots of commentaries on it. In fact, the commentary of Bhaskara 1 has been the one which has made us understand what Aryabhatta did. And there are many more things that Bhaskara did. He also came up with a very beautiful formula as a ratio of two quadratic functions for sine. And this makes sine calculation very easy. It is accurate up to 1% for the entire range from 0 degrees to 90 degrees. It's a formula where sine is expressed as a ratio of two quadratic expressions in the angle. Then the works of Brahmagupta are extraordinarily important because while Aryabhatiya is a very cryptic text, Brahmagupta wrote a very detailed text of astronomy. And in fact, most of our current understanding of Indian astronomy and mathematics is from the Brahmasputa Siddhanta of Brahmagupta. Unfortunately, the most important commentary on Brahmagupta's Brahmasputa Siddhanta is yet to be published and translated. Brahmagupta was the person who discovered negative numbers in a formal sense. Earlier, negative numbers was used in the sense of debt, and even in Chanakya, you have some idea of that. But Brahmagupta gave the rules. -1 into -2 is +2, or minus of minus is plus, and many other things. And 0 also was treated. He started algebra by giving symbols to, instead of x, y, z, he used ya, ka, bha, etc. So algebraic polynomials. And he even discussed very complex equation. I will not tell you what it is. He discussed cyclic quadrilaterals, and he discussed spherical trigonometry. Aryabhatta was the founder of spherical trigonometry. Brahmagupta used entire spherical trigonometry in writing his textbook of mathematical astronomy. So his mathematical astronomy was full of formulae. Only the formulae were written in terms of verses. For the rest of the world to get to all this level of sophistication of astronomy, it took at least 500, 600 more years. It made it possible for Indians to even write other kinds of approximate manuals called Karana. Once you have formulae, you can work out approximate formulae also. Oh, there was this Virahanka, in his work on prosody or chandas, you have these Fibonacci numbers appearing for the first time in 6th century. Now I will rush through. So around 650 is when Indian mathematics went to West Asia. But actually much before that it went to East Asia. I think China adopted Indian astronomy around 500 and Buddhism even 200, 300 years earlier, around 2nd century BCE. In fact, it was observing in the Chinese court that they were using Indian astronomical methods for calculation, that the Baghdad Caliph asked for Indian astronomical texts to be brought there towards the end of 650. So it was the Harun al-Rashid, but his father, I think Mansur, they got Indian text translated. And for about 100 years in the Islamic region, Indian astronomy and mathematics was the primary text. They started translating Ptolemy around 750. But since philosophically their view was more close to the Greek view, they adopted the Ptolemaic text, but used the Indian methods of calculation to do all their astronomy. Now we have various books of famous authors, Mahaviracharya, Sridhara, Lalla. Mahavira's Ganitasara Sangraha, he was a Jain in Karnataka, is a work of about more than 1,500 verses, entirely devoted to mathematics. Earlier mathematics was with astronomy and other subjects. Prutudaka Swamin Vateshwara, so the list is long, but we discovered the idea of what is called instantaneous velocity of plane. That's a very complicated concept. A car moves 10 miles an hour, so it moves 5 miles in half an hour. It moves, so like that you can go on, but the idea of instantaneous velocity is assuming that for a very short while, how much the car would have moved, you have to find out what its velocity would be when its rate of change of position is not uniform. Similarly, this was a very complicated algorithm, Chakrawala, discovered by Jayadeva, which solves a quadratic indeterminate equation, which was rediscovered in Europe in 17th century. But the method that was discovered in Europe was inferior to what Jayadeva had done in 1050. So that's the kind of advances that was there. Bhaskaracharya's name all of you know, but these three texts were the most important texts by being treated as a textbook all over India during the next 500 to 800 years. In fact, many regional language texts adopted what is there in Lilavati and Bijaganita. There were several regional language texts that were written starting around 1100 in the field of astronomy and mathematics. Regional language texts in grammar are known from 600 or 700 onwards. So Mallanna had written a mathematics book in Telugu, which is a translation of Mahaviracharya. There's a Telugu commentary on Surya Siddhanta. Vyavahara Ganita is a Kannada work on mathematics. This is the Tamil work on astronomy. And this is a Prakrit work on astronomy, etc. Now we come to the medieval period. The general feeling is that astronomy and mathematics, everything in India closed around 1200. That's not really true. There was, of course, a certain retardation in the northern part of India because the rulers no longer valued the Indian civilizational learning. But that doesn't mean that Indians gave up their system of education or system of learning as long as that was not actively disrupted by the rulers. So there is a continuous tradition of work in North India also. Narayana Pandita's Ganita Kaumudi, which Professor Ram Subramaniam talked about, this is about 4 times the size of Lilavati and it has 4 times more the content. And he did some things which are very closely related to calculus, like what is called repeated summation. He worked on combinatorics of very permutations, combinatorics of binomial coefficients, which were all treated only in 18th, 19th century Europe. Then a whole lot of astronomers who started writing older books. The older books were somewhat short. So the way the teacher taught them must involve a whole lot of explanations and proofs and all that. But we do not have those commentaries. But we now have for Bhaskaracharya various kinds of commentaries written by these people which give very detailed explanations and proofs. We also started taking various inputs from Islamic astronomy that you can see in the works of Nityananda Munishwara. But the most important person in North India was this great person who may really be called the Renaissance person in Indian history in recent times, Savai Jaisimha. He built these 5 observatories in Ujjaini, Delhi, Mathura, Varanasi and Jaipur. Mathura thing was destroyed in 19th century. The Delhi one is used for conducting demonstrations today. Jaipur is a very nice observatory which you can go and even see today. But the Banaras one is in a sort of very dilapidated condition. It's in that Man Mandir Ghat, you have to go around and see. But these observatories were the most accurate ones. They were accurate to 1 second of a minute. 1 minute of arc, that is 1/60th of a degree, which is the best accuracy you can obtain by naked eye astronomy. That was the kind of accuracy that was there. He got works from Persian translated. The Ptolemy's work was also translated from Persian, but he got the French tables of De la Hire translated, and then he used them to do observation with his observatories, put them to observational test. And he wrote to these Jesuits saying, I am finding these discrepancies in your tables. So I don't understand that. Maybe I have not understood what it is. You come and explain it to me. So he was trying to redo the older texts of India by borrowing some of the elements from whatever others had done and putting all that to observational test. This is the most important part of most science, that there has to be observation, there has to be sort of interaction with what can be called advanced knowledge all over the world. But all that with a view to update our own knowledge in such a way that whatever we finally arrive at is in consonance with what we observe and what we need. In that sense, Savai Jaisimha was a very great man. Now I come to the other section, this last 3 minutes only. I'm very sorry I've taken more time. So this is what is well known as the Kerala school. It was started by this person called Madhava. And he, around 1350 or 1370, he discovered this infinite series for pi, sine and cosine functions. Not only did he discover them, he also found out very close approximations for them. He also improved what is called the Vakya method. Then he also wrote on spherical astronomy. His student Parameshwara is known for 55 years of continued observations. And Parameshwara's student, Nilakantha Somyaji, was the person who came up with a revolutionary change in the planetary model that was used in India. And this change was such that it made the Indian calculations computationally to be the same as what came about in Europe 200 years later in the models of Kepler. In fact, his computational model was better than that of Copernicus and Tycho Brahe. It was as good as that adopted by Kepler in early 17th century. But it was not revolutionary in India because he explained his model in relation to the older model and the observations he had made in such a way that the transition was very smooth. There was no debate in India whether sun was the center of the world or earth was the center of the world. We knew that such questions cannot be merely answered by speculation. If at all we have to say something, there has to be an observational basis for it. And then this text in Malayalam is the lecture notes of all these people, and that contains very detailed exposition of explanations and proofs. It was written in 1530. It's called Ganita Yukti Bhasha. So regional language literature is not merely a transcription of Sanskrit literature. Many times it has something extraordinarily original, like this text Yukti Bhasha written in 1530. The Kerala school continued. Of course, as you know, the Kerala coast became infested with Portuguese and Dutch by about 1500, and by 1550 this learning slowed down, but it continued till about 1819, when actually most of Indian learning really started coming down. When British did a survey of Indian indigenous education in Kerala, they found almost about 600 to 700 students studying advanced mathematical astronomy. And most of them came from diverse communities. And this was the kind of development. The last two slides. These are the history of exact results of pi. And you can see these series that Madhava wrote down. Many of them have been repeated 200 years later in later discoveries. And this was a very seminal work of Ramanujan, which is very similar in spirit to what was done by Madhava. And it was revolutionary in its time. It was used to calculate pi to 1 billion places around 1980. Similarly, in the history of planetary models, you can see this continued development from ancient India. And Nilakantha comes somewhere here, and what he did anticipates what Kepler did. So to conclude, Indians were not wanting to do what Westerners did later. That's not the way to look at it. Or Vedas are not written to tell us how to advance modern cosmology or modern theories of cognitive science. That is not the purpose for which they have been written. So we have to first understand the larger purposes for which it is written. In practice, it may have many inputs. Like the benzene ring, I am sure you remember that Kekule discovered it during his dream. Or it is said that the person who discovered periodic table, Mendeleev, he saw this Varnamala, and it again occurred to him in a dream that the elements can also be put there. But the Varnamala, A, I, E and Ka, Kha, Ga, Gha, Nga has nothing to directly to do with the periodic table. So we can always derive ideas from our own civilizational resources. But that we can derive only if we happen to know them. But more than that, our civilizational resources tell us the essential civilizational values, the purposes for which we did many of these practical things, and the way we achieved them. With the practical things, the good thing is, we would have abandoned if it didn't work. So only whatever worked got passed on, researched upon, expanded upon in thousands of texts on Indian knowledge that's available in India. And I think that will be the purpose with which we should look at them. And that will be the purpose with which we should interact with modern knowledge and go on adding to our corpus so that we can talk of an Indian school of science, if not an Indian civilizational science, in the next generation or two. Thank you very much, and sorry for the time I take.